In other words, are you able to get some data, push it through a system, get an answer, and do some evaluation? The actual evaluation you get is not going to affect the score you get in the assignment, but it is interesting. You're getting some interesting observations about what's happening, and hopefully it'll be something we pick up on and discuss further as we go more into the course. But for now, the only goal of this was to make sure you understand this. In further assignments, I'm going to say, okay, run a clustering on this data, and I don't want, and by after the assignment, it should be easy for you to do that kind of thing because you've already done it once. Okay, so don't worry about whether you've got the right answer, if their answer is correct, and if the answer is what I wanted. The only answer I wanted is that you have an answer. Okay, so the deadline again is today at 5 p.m. Upload a PDF or something converted to a PDF, preferably, LaTeX or whatever. And I know you've all been putting in links to the data sets, which is good because for future assignments, you're going to mix and match. So you're going to use someone else's data set, they're going to use yours, and so on and so forth. So it'll be fun to play with these things. All right. So any other questions about the assignment in the last few hours before you have to submit? Any? No? Okay. Good. So let us recap. So what did we talk about last? Anyone? People were over here. I know some of you weren't here last time.
Hierarchical clustering.
Okay, so good. So tell me about hierarchical clustering. What's the deal?
You basically.
So your name is
James.
James. Sorry.
Yeah. You basically cluster kind of like a tree, and you can either do top down or bottom up clustering of those elements.
And why do we want to do hierarchical? What's the big deal here? Why should we even talk about it? In your view? I mean, either what I said or what you think. What do you think?
I'm trying to remember what we
sure.
were talking about, but.
You want to? Okay, so yeah, go ahead. Yeah.
You have two C's, those kind of. You have a C and then another C. Those kind of clustering are not captured by
That is true, but is that why we use hierarchical clustering? Because I could probably design a clustering that, and there are other ways to design clustering algorithms that would be able to capture those kind of shapes. But I think maybe more than that. Does anyone would like to chime in? Yeah.
That you get like a full family of possible clusterings. That you don't get enough data from one single clustering, but what you wind up with here is a whole set of possible clusterings that give you a varying way of looking, or basically an ensemble of views into the data set.
That is correct, with one caveat, that there are many ways to get an ensemble of clusterings, but there's something special about hierarchical clustering.
I mean, the word itself is here, it's present, right? It's the
It's
relations. It's the relation between the clusters.
Tell me.
And
What do you mean by that?
what I mean is the clusters, so it's not the parents, the predecessors.
Yes.
Or
But you can use parents of the tree.
Yeah, so the idea is that the parents of the tree, the children contain the points of the children, obviously.
Yes.
And, so it's kind of a navigation down to the clusters, and it's just a very good property to have.
Any other thoughts on this? Yes?
A little bit about topology features.
Louder.
Oh. Topology features.
Yeah.
Hierarchical orders, so you have topology.
So are you familiar with the topological approach to clustering? Are you familiar with persistence?
Not yet.
Not yet, but you've heard about these things. It's something I want to mention later on. Okay, good. All right. So all of these answers are, getting at why we look at hierarchical clustering. One point that I wanted to emphasize again, just because it didn't explicitly come up in the conversation, was that, we have this free parameter in clustering, the number of clusters you want. And one of the things hierarchical clustering tries to do is get around that issue. Is to say you don't have to choose a particular value of k. We give you an ensemble, but an ensemble that is, in some sense, gives you answers across different values of k. I mean, there are many ways to construct an ensemble of clusterings. I could construct an ensemble of k clusterings. I could run k-means with different initialization and get different answers. That would also be an ensemble with different views. But it wouldn't be an ensemble across k. And that's one of the things that hierarchical clustering gives you. And as Clement mentioned, the hierarchy part of this is also important because then it gives you a sense of the evolution of the clustering. That if you believe what's going on with the data, it's trying to tell you how the data evolves and blobs up into chunks, which maybe gives you a bit more structure to the data than just a single snapshot. All right, so we talked about different ways of doing hierarchical clustering. We said, first of all, okay, how do you represent a hierarchical clustering? For a regular clustering, that's easy. You just have a partition. But for a hierarchical clustering, you need a hierarchy, a tree. And a tree that says, okay, at the top, there's some node which corresponds to everything in one blob. At the bottom are leaves where everything is by itself, and then you merge things up. So every internal node of the tree is associated with some cluster. And so if you take a cut along the tree, you get a clustering. And so you can get a whole family of clusterings. So once you have the notion of a hierarchical clustering and the notion of a representation, you can now ask, okay, how do I compute such a thing? And then you can ask questions about cost and so on and so forth. And so we didn't actually talk about costs in particular yet. We just talked about ways in which you might go about doing this. We talked about divisive methods, where you have some oracle that gives you a clustering, like say k-means. And so then you apply that oracle with k equal to 2 or 3 or 4, and then you recurse. And that's one way to do things. And the other way I mentioned, which is more bottom-up, is you start from the bottom, and you kind of merge things together. And you group things together that seem like they should be. So it's like the opposite of k-center. In k-center, we were trying to find things that were very far apart that could represent cluster centers. Here we're saying find things that are very close that probably should be in a cluster. Right? And then we made this observation that I mentioned, that if you have, that one of the good things that one example of this called single link clustering can do. Single link means take 2 points and see the distance between them. If you have 2 blobs, take the closest distance between them. And then always merge the 2 blobs that are closest to each other. Right? So you get these blobs together, so you get this whole hierarchy forming. And one thing this in particular can do is capture long stringy clusters. Right? So if you have one cluster that looked like this, another one that looked like this, most clustering algorithms that you have seen so far would fail to find this, because they're trying to find patches of space. Whereas this is not trying to find, it's trying to find local connectivity. So in that sense, it is a bit more, for lack of a better word, topological, in the sense that it's not looking at the entirety of the space, it's looking in a small neighborhood around it, and saying, you know, who should I absorb next, because of the single link property. And so it's able to trace all these things. Okay. So I think we stopped roughly around single link clustering. I don't think we went beyond this. We talked about other ways of merging things, but I don't remember us discussing these. So let's continue from there. So as I said, the first method we have for doing agglomerative clustering. So we're talking about hierarchical agglomerative clustering, HAC, where the idea is that you do it bottom up. You have some notion of how close 2 blobs are, where a blob starts off being a point and ends up being the entire thing. And then you say, okay, once I have a notion of how close 2 things are, I say always find the closest pair of blobs and blob them together, and then repeat. And so all I have left to do is define a distance between blobs. And so we said single link was the distance between 2 blobs, which we'll call 2 sets, is equal to the min, A belonging to A, B belonging to B, distance A comma B. Right? And one of the good things about this definition is that all I am using here is a notion of distance. In fact, I'm not even using triangle equality, but let's just say we have it. So this works in a metric space. You don't need a full, nice vector space structure, or Euclidean structure, or what have you to do this. This works regardless. Now, because single link has this somewhat aggressive property, just find something close by and latch onto it, it also has this problem, and we'll see this more formally in a bit, that it can latch onto things that it probably shouldn't. It can be too aggressive about finding connections. Like, for example, if it sees a point that's maybe close by here, it just jumps straight onto it and then just hooks up the whole thing into one blob, and maybe you don't want that. So an alternate, a variant of this, which is a bit more robust, or maybe a lot more robust actually, which is called complete linkage. Right? Does the pessimistic version of this. And again, you have the distance between blobs. So what do you think a pessimistic version of this would be? Not a robust, but a really sort of a very grumpy version. Like a version of this without coffee. Something very similar to this, but slightly different. Max. In fact, that's what it is. What does this do? If single linkage could be drawn with this picture right here, right? Complete linkage with the same picture would be drawn like this. Right? Because you're only going to put things together if they're really close together. For those of you who are familiar with computational topology, there's a what's that called? Ribs complex, check complex sort of connection. I'm not going to get into that. If you don't know topology, you'll know what you're talking about. And if you do, you just might think I'm being silly. But okay. But there is a sort of, there's a worst case versus best case kind of argument going on here. That in the single linkage case, you just need one link to witness the fact that two things can be put together. In complete link, you can think of this thing, you only need one link to witness the fact that they should not be put together. Right? You need everything to work well for them to be put together. If you want these two to merge, every pair here has to be closer than any pair in some other cluster. Right? So obviously, complete linkage will give you much tighter balls. You will not get this kind of stringy structure because by the time you get, like, say, this much in complete linkage, if you want to merge in something, you're going to pay this as your cost. Whereas maybe something else is maybe easier to do. You might prefer to do this instead. So complete linkage is going to give you something which is closer in some sense to what traditional clusterings might give you, while still able to navigate around strange shapes. And in some sense, that's one reason, I think, personally, why single link is so popular. Because single link does something that's fundamentally different. Right? This long stringy cluster. And maybe you do want long stringy cluster, so it gives you that. Other methods that are not so aggressive get you back towards more traditional ones when you could just use a traditional link. That's just, again, my personal opinion. Once you have the min and the max, the obvious thing to say is, well, I don't want the min, I don't want the max, I want something a bit more, average. So there's obviously something called average linkage. And you can imagine again that now, so in other words, add up all the pairs of distances, divide by A times B. Okay? And if you had to draw this picture, again, this is loose, but you might think of it as something that looks like this, roughly. And in fact, if the distances you were choosing, if this distance happened to be Euclidean distance squared, if your points actually happen to be in Euclidean space, and you wanted to do this, what you'd end up with is, you can prove this, is something that looks like this. So of course, once you get to this final definition here, we are now making assumptions about our input. We are now saying our input lies in a Euclidean space, right? Because otherwise I can't even define this notion. But for Euclidean data in particular, this is a very handy notion to have, because now if you think about the efficiency of computing these objects, all these things can be very expensive to compute because you have to look over all pairs. This is much easier. It's linear. Just maintain. In fact, if you maintain the centroids carefully, it will be even less time. So this also has some nice properties because of the efficiency of working and the fact that it gives you these representatives. So you can actually just store the representatives because it's easy to say, okay, what happens to centroid if I merge two things together? If you take one cluster with one centroid, one cluster with another centroid, and the centroid of the new cluster is just the weighted mean of these two based on the size of the size. So from a representation and algorithmic perspective, this is a very pleasing notion if you have Euclidean data. So there are other ways you could imagine doing these things, because in fact, that's why I said that all you need is some kind of rule to combine blobs. As long as you have a reasonable rule to combine blobs, you can run a version of hack. These are just some of the more popular ones that people tend to use. So if you hear the name, you should know, okay, if they're doing centroidal hack, they mean this. Yeah.
So the complete link, we find the maximum distance from one block to every other block, and then decide which block to merge it with.
Which one are the closest to under that notion of
So
distance?
it's min of max is the
So everything is it's a min of this. So in other words, you look at the min over all pairs of blobs, where the distance for each blob is defined by this. So yeah, so there's a double pairwise thing going on here, right? It's for each. That's why it's very important to make these fast, because in any case you're gonna have to work over pairs of blobs. But the thing is, eventually, very quickly, you're going to reduce the number of blobs, hopefully, to the point where it's not terrible. In the beginning, it's bad. Okay? Yes?
The average link and centroid are not completely equivalent, right?
They're equivalent if this was the Euclidean distance squared. Otherwise, they're not equivalent. If this was even Euclidean distance, then it's not the same thing. This centroid shows up from the fact that that the average, basically it's this whole bias variance thing, right? That the average sum of squared distances can be written in terms of the centroids, distance of the centroids and some other distance.
Right.
That's where this comes from.
So if that distance is a squared Euclidean distance, then they are equal.
Squared Euclidean distance, yeah. Okay, I don't know if they're equal so much as equivalent. In other words, there's a monotonic transformation between them. There might be factors of 2 here and there hiding, but they're equivalent in that sense. You'll get the same results if you want to. Okay, any questions? Okay. If I were to stop here and say, okay, this is what we know so far about hierarchical clustering, what questions would come to your mind about it? What do you think you'd want to know at this point? I'm just curious. Coming from yesterday, from last lecture and today, everything I've told you so far, what do you think you might need to know?
When do we stop?
Sorry?
When do we stop?
When you have one, when everything's in a blob, you're forming a tree.
This question is regarding hierarchical clustering. I would ask myself, how do we merge? Why do we always merge 2 of them?
Why do you always merge 2 of them?
Yeah.
As opposed to?
As opposed to, I don't know, figuring out what
What?
would be the right ratio of merging them.
What is the right ratio for merging?
I mean, like, why would we necessarily have a binary tree, right?
What would you rather have? Well, what do you think would be useful to have?
Is it the bottom out cluster? Have you talked about the other?
Yes. So there, I talked about this last time. So basically, assuming you have some oracle that does clustering, let's say k means, whatever you want from oracle, right? Then you could set k equal to, say, some small constant, like 2 or 3 or 4. Run it in the top down. Now you get clusters. Then you recurse those. And then you just get them.
Let's say you have 3.
No, because we talked about it already.
So let's say you have 3 clusters that are about the same distance apart, right?
Yeah.
So why would you prefer to choose these 2 or these 2 or these 2 pairs? Or not all of 3 of them at once?
There is no real reason. In fact, I mean, yes. So if so the example here is this. So I have one blob here, one blob here, one blob here. What you're saying is that it's called and they're basically 3 equivalent trees, right? So there's basically
Yep.
and then that's what you're saying. You could think of this as either of these 3 trees, and there's nothing fundamentally different about them. So this boils down to a tie-breaking issue at some level. Right? If there are things that are very close, is there a systematic rule for tie-breaking? And the point about hierarchical clustering is that what you get, especially if these things are close, that this is very arbitrary, this choice of which way to go. It can look very different in the resulting tree, but it may not be. And we'll get to this in a little bit today, about what you might be able to do with this. Not algorithmically, but at least visually, how you can deal with this problem. So I'll talk about that.
And we build a tree that is fine, and supposing we want k clusters, and we can cut the tree in many ways. So what could be the correct tree?
What is correct? The premise of a hierarchical clustering is that you don't believe that there is one correct answer, because if you did, you'd go look for it. The premise of hierarchical clustering is that you believe there are many answers and you wish to explore them. Right. So in other words, I'm not doing hierarchical clustering because I want to find one cluster. I'm doing it because I want to find many of them. Like if I then want to go search for a particular one, I could take whichever one I wanted, or I could just run some other algorithm just directly finds the best K for a particular table or whatever I want.
Okay, so we run hierarchical clustering, we get n different K clusterings, and we, for each one of them, you again compare with the ground truth. Compute,
You could.
take the card index and find the best one.
You could, yes. Well, you could do that again. And again, remember the goal here is not to find one answer. The goal is to see whether all these answers together give you a picture. But one thing that comes up here, and this somewhat relates to your question, is that you could, and you probably should be asking yourself, that's all very well, but how good are these clusters?
What's happening with outliers?
Sorry?
What's happening with outliers?
What's happening with outliers?
Because you're grabbing more and more.
Yes.
And you're doing very greedy approach.
Yes, you are.
You don't have some global picture of it. I think you can get lost really fast.
You can get lost because of outliers. I would argue
Maybe not
that
just,
in fact,
maybe not just because of
so let
outliers.
me, so while I think outliers are an important problem that are in some sense orthogonal to this particular thing, I would argue that hierarchical clustering makes it a little bit easier to get outliers rather than harder. Because what's going to happen if you have outliers in your data? Right? If you think of a bunch of points, so I have my clusters here. Let's say this is my space where the clustering is sort of reasonable, and I have a bunch of outliers here. What is my tree going to look like?
You will add those points at the end.
At the end. You'll have a little sort of branch coming up right at the top of the end, which is not really merging up and getting bushy, but it's kind of straddling by itself. So in some sense, it might even be easier to find outliers with this than any of the methods we've seen so far that are aggressively trying to put them into blobs. So it might actually work better. I don't think there's a proof of this, but I think it's something that that is something that's attractive about these methods. But getting back to the point I was making is that we don't really, what we'd like to know is, well, how good these are. And what does that mean to say how good they are? So one way to ask the question is this, is to say, I claimed that I wanted a hierarchical clustering because it gives me a larger picture of the data. But implicit in that claim is the idea that if I did look at a snapshot, it would be a pretty good snapshot of what I would have got if I had just run a K cluster. Right? If I look at the hierarchical clustering and looked at a 2 clustering, then it would be reasonable compared to the best 2 clustering I've got. This is what's the point. If I get a bunch of crap clusterings, the fact that they give me an overview of the data doesn't help me very much. I would like it to be somewhat reasonable compared to the actual K clusterings. And this is where things start getting interesting. And now you can start being a little bit more precise. You can ask questions like, how does a hierarchical clustering compare to the best K clustering? And so in particular, you can say things like this. You can say, so take a hierarchical clustering. Right? And then compute all the, we'll put in quotes, canonical K clusterings from it. And what I mean by this is that I have a set of points, which are, you can think of as being an n clustering, there are n points. And think of, again, bottom-up hack right now. I merge 2 things. So now I get an n minus 1 clustering. Right? So I have the first clustering, which is the input, which is, we'll call it Cn. I do one merge, and I get Cn minus 1. I do another merge, I get Cn minus 2, all the way up to C1, which is everything in one set. I should have, this is X, and this is basically all points. So it's a set of all X. It's a set of all individual clusters. So you can think of this canonical clustering you get from the merge process. Set of clusters you get. And now for each of these, you could say, okay, let's look at the best n minus 2 cluster under whatever metric you're using. So between a single metric. And I can compare these two. So it gives me some comparison number. Let's say I take the ratio of their costs, right? So this gives me some cost, this gives me some cost. This cost is obviously going to be better than that because it's the best one. So I take this ratio, and I call it, say, alpha n minus 2. Then I have alpha n minus 1. And I have alpha n is just alpha n is 1. And then I have a bunch of stuff here. Right? So this is again 1. Right, so I have the sequence of numbers, right? And now I can say, let's say alpha is equal to the max alpha. In other words, one way of asking about how good a hierarchical cluster is to say, in the worst case, how far will it be from the best single snapshot clustering you could have run? Okay. Now what can we see? And it turns out that for all the methods that people like to use, they're all terrible. And you can prove it. So let me give you, so just as an exercise, right? Let's look at single link clustering. I claim it's actually very terrible compared to the best possible clustering you can get. Can you sort of posit or throw out or speculate or conjecture on what might be an example of a set of points where this will do really badly compared to what the best thing would do? Because sometimes the examples are useful because they're not just constructions for a proof, but they give you intuition as to where these things fail. Any thoughts? So where do you, I mean, again, this is an important sort of skill to have, right? When you take, especially with clustering, when is it going to fail? So when do you think single link in particular is going to fail badly? In terms of, what it is doing versus what you think it should be doing?
When two clusters are very close together, but they are sparse rather.
Two clusters are close, but they are sparse. This is a good intuition. Can you build it up into an example? This is a very good intuition.
Like, yeah, right, two circles.
Two
close
circles.
to each other.
Yeah.
But very sparse.
Okay, so what will happen?
Because they are close together, then
Yeah.
single link, and they are sparse, then single link might consider them as one cluster. But I mean, you can extend that to more clusters.
Right, so the question is, can you do more of that? You're on the right track, but you just got to simplify and extend. Sorry?
Like if two clusters are closer together and then the sparsity causes the internal components to be farther away.
Yeah,
it's
yeah,
gonna,
yeah.
It's going to link.
Okay, let's make it
between
even
all
simpler.
the clusters.
Suppose you have points on the line. It turns out you can find bad example on line. Huh? Each point is away, but okay. So here's a very clever construction that comes from this paper that I mentioned in the notes, or when I give it to you. So think of points just sort of on the line, and as they get further out, they get kind of closer. Okay? This is an example that both of you have been trying to allude to. And in fact, in the paper, there's a formal way to say this, that basically you say the distance from point J to J plus 1. So the distance from J to J plus 1 point is something like J epsilon. If you don't like what this means, basically think of it as it's 1. It should have been 1, but it's getting smaller as J increases. So as they go further out, it gets smaller and smaller and smaller. Epsilon is the rate at which it gets smaller. Okay, so if this is my example, what is going to happen first? What's the first thing that single link clustering is going to do?
It's going to link the
Furthest 2 points. What's it going to do next?
then link the next. It's just going to go straight down the line.
It's going to keep going straight down the line. Okay. Let us stop at the point when there are k clusters, because we want to compare to say alpha k. If you can prove something generic with alpha k, we can reason with alpha in general, right? Okay, so let's say what happens. Let's stop at some alpha k. So what's going to happen at the alpha k position is that you're going to have k minus 1 points here, all getting slightly closer to each other, and then you're going to have a blob of everything else. This is what single link clustering is going to look like. Okay? Let's say now, because of the way single link works, that we're trying to measure so the diameter of this cluster is our cost, like a k-center cost, right? So what's the diameter of this cluster? We don't quite know what it is, but we know that it's just basically sum of 1 minus j epsilon for j going from k minus 1 to n. If you choose epsilon small enough and squint it and just sort of murmur a few prayers, this will basically be something like roughly n minus k. If you don't believe me, you can calculate exactly. It'll be n minus k minus basically summation of j from k to n times epsilon. If you make epsilon something like 1 over n squared, it can be ignored, and it's roughly this. Okay? and then each of these are whatever they are. So the cost of this clustering in the k-center notion is going to be n minus k. Okay, but what's the cost of the best k-center clustering of this algorithm? So if you run Gonzalez on this, for example, what are you going to get? What's going to happen? What's going to happen is that you're basically going to pick, this is going to be one blob, this is going to be one blob.
Equal space intervals.
Equal space interval, exactly. And what's the diameter of each of these going to be? Remember, there are k clusters. So each blob has size roughly n over k. And again, squinting a little bit at this j, it's roughly diameter n over k. Okay? So basically now we're comparing, so if you write this down, single link is giving us a cost of n minus k. Best k clustering, or better at least, is giving a cost of n divided by k. And again, in the limit, as n gets very large, this ratio is roughly k. So in other words, you can be a factor of k away from the best possible answer. And this is bad because as k changes, your ratio changes as well. It's not even a constant factor. It's a factor that changes with k. So single link is terrible. Okay? In terms of doing anything, from a point of view of you actually extracting something of quality under some measure. You can do something similar for complete and average linkage. It's a bit the constructions are a little bit more intricate because of these properties. It's harder to fool them. So you have to be more clever, but you can. And the corresponding ratio, and again I'll link to a paper that sort of shows this. It's a bit more involved. Is not k. It's a bit better. It's something like log k. So it does grow with k. It grows more slowly, much more slowly, of course, but it still grows with k. So it's unbounded, the error. So we're in a kind of dissatisfying state of affairs where we have an idea of hierarchical clustering. We have a bunch of methods, but we know they don't do very well compared to what the best snapshot would be. So either we have to compromise and say, well, okay, I'm still getting a hierarchy and I'll have to live with this, or ask ourselves, is there any way to do any better? And it turns out you can do a lot better. And it turns out it's not particularly hard to do a lot better as well. The basic algorithm idea that works for both k-center based cost measures as well as k-median based cost measures. In other words, my cost of not the max, but again the sum of the distances, just like in k-median, you can still show something reasonable. And the basic idea, and again this is in the papers that I will link to, is that you have to construct the right kind of hierarchy. Okay? You can't just use a blind single link type hierarchy. That'll cause you trouble. Okay. And so the one algorithm that gives you a very good result for single. So to give you the punchline first, there is a hierarchical clustering algorithm. There's a hack algorithm under the k-center objective, which means that you measure the cost of a clustering by the max diameter, such that the result you get, that alpha, is equal to 8. It's constant. So in other words, if you take your hierarchical clustering and produces canonical clusterings from it, any one of them is no more than a factor of 8 from the best possible one you could get. Remember, Gonzalez gave you a factor of 2. So this is 4 times worse than that. But it's still a constant, and it's independent of the number of clusters, number of points, whatever. And the basic idea here is not very hard. What you do is, step 1 is run Gonzalez. Okay. In other words, run the k-center algorithm to get these centers. Okay. And then, so once you get these centers, you get a bunch of points. And now you can attach points to these clusters as being sort of owned by a cluster. So what you can do is you can say, okay, let me back up a second. So here's one way you could have tried to do this a bit more cleverly. You could just run Gonzalez, say, from 1. You get the first point. So everyone is in that cluster. That's your top node. Then run it for 2. And now points cleave off into whichever the nearest neighbors. That's your 2. Then run it for, then get the next center. So now you have 3, and now things cleave off. This doesn't give you a hierarchical cluster. You can construct examples to see this, right? That the points might be here, they might split up, they might join up again. So you can't just, so what you cannot do is just run, get a center. center, then take off some of them, and take another center and take off some of them in a kind of divisive way. That won't work. You have to be a little bit more clever. Okay, so you still run this initialization step, but what you do is, and again, the technical details are kind of a little bit tricky because you have to, because of the way you have to do the analysis, and I'm not going to get into that here. What you do is you, how shall I say this? Right. So pretend you're running Gonzalez all the way to the end. So in other words, you get to the first point, then you get the second point. So call this distance R1. Right. Then you get the third point somewhere, and now call this min distance R2. So you get distances R1, R2, up to Rn minus 1. Right. Distances that tell you what the distance to the next center was in your list. And then what you do is you break up these distances into chunks that are sort of factor 2 apart. So you say, okay, there's R1, you go from R1 up to 2R1, then you go from 2R1 up to 4R1, and so on and so forth. It's exponentially increasing. And then what you say is that you essentially, you attach points to the closest neighbor in the previous level. So this is one level, there's another level, there's another level, there's another level. You attach points to the closest neighbor in the previous level to them. And it turns out that if you do this in a slightly modified way, you can actually prove that you necessarily don't attach points together, they're going to be split up. And you can get this factor, basically you get a factor 4, and then Gonzalez gives you a factor 2, and you get a factor 8. So again, I'm deliberately not getting into the details of this because a lot of this is technical analysis. But the basic idea is that you build some kind of hierarchy and use a little bit of surgery on it. You don't actually take the hierarchy as given to you by single link or something else. And I'm actually a little bit surprised because these modifications in the algorithm are actually quite simple. They're not very hard. The analysis is what's complicated, but I haven't seen too much work on actually trying these things out. In fact, one of the papers I will point out to you is a paper that actually does a detailed empirical analysis of different kinds of hierarchical methods with different underlying base methods and seeing how they do and getting some results of that. So it's kind of interesting to see. So that's for the k-center objective. You can do something similar for the k-median objective. It's again a very similar idea. You start off with some base hierarchical clustering and you do surgery on the tree and then you re-merge things up in the right way. There the bounds are a little worse. I think the approximation ratio you get for this, the first algorithm, was unstated in the paper, which basically means it's very large. Another paper worked it out as something like 200. Still a constant, but it's a very large constant. And I think this has been brought down over time to something like 20. And if you're willing to be randomized, you can get slightly better. So it's not great for k-median. It's much better for k-center. I should say that using a somewhat randomized trick, you can get this down to 5. 5.4. Using randomization. But again, I won't mention that. So the good news is that there are some results you can get that say that if you take hack and modify the algorithm you get ever so slightly, you will actually be able to get a hierarchical thing that has some formal guarantee with respect to the best possible. Okay. So this will all be the notes. I'm almost done with the notes now. Handed out today. Okay. Any questions so far before I move on to the next sort of subtopic in hierarchical clustering? No? All good so far? All right.
So I have a question.
Yeah.
So the way that we start the cluster is take the two closest blob
Blobs, yeah.
and join them.
Yep.
Take the next closest blob to take the next two closest blob. Again.
No. Take the two closest blobs, join them. Now you have one blob. You've taken off two blobs, you put in one blob.
Yeah.
Again, I have a bag of blobs. Do the same thing again.
Yes.
Right. So not the next two.
Okay.
Yeah. What I mean is you start again. Yeah. Find the next two. Could be this one and the one again.
Yes.
Right.
So okay, it can happen that we join the next two.
To this one.
Yeah, to this one
Or something else. Yes. Absolutely. Yeah. Okay. Any other questions? Did you have a question? All right. So one of the other reasons why hierarchical clustering, it's very hard to say this fast, hierarchical clustering has been so popular is that it has lent itself to very nice visualizations. Now, visualization is something we haven't yet talked about in this class. And in fact, we're going to talk about this a bit more next lecture. Because one of the things I argued about what makes clustering interesting is that it's an exploratory tool. It's a tool you use at the beginning of a process rather than at the end. You might use it at the end too, but you most often use it at the beginning of a process and analyzing data. And therefore, what you really want to do is see the answers you're getting, right? And as you've probably found out, it's very hard to see a 10 cluster. If you're taking some data and you're clustering it, it's very hard to see. All these things we do, the random links, the Jacquard, are kind of backdoor ways of trying to get at what's going on. What you really like to do is just see it. And since we can't see in 10 dimensions, it's very hard to do, right? And we'll talk next few lectures about how people are trying to how people try to visualize the results of clustering. Basically by using various kinds of embedding and dimensionality reduction techniques. But hierarchical clustering lends itself to a very different kind of visualization that has become extremely popular, especially in the evolutionary biology and genetics literature. And it's this thing called a dendrogram. And it takes advantage of the fact that the object we construct is a tree. And that the tree itself has some nice structure to it. And again, those of you who are dabbling in topology will start seeing some similarities here to things like ring graphs and contour trees and stuff. Maybe I'm jumping in. So what is a dendrogram? So a dendrogram is basically a glorified version of these things I've been drawing since the last lecture. Trees. The idea is that if I want to describe a merge process, so I have, let's say I have 10 points. Okay? And I want to describe their merge. What you do with the dendrogram is, instead of just drawing a regular tree, you draw them up kind of vertically. So maybe your first two things that merge are A and B. And then maybe C merges with that. Not probably running vertically very well, but you get the idea. Maybe the next two things that merge were E and F. And they merged, okay, so they after this all happens, they merge. So we're going to draw them up here. Notice I'm already doing something different. I'm not like drawing them down there, right out there. And then this merges with G. And then maybe H and I merge. And then J merges with that. And then now, these two merge. And almost immediately after that, these two merge. And then finally, there's a merge at the top. This, of course, is a tree. Nothing special about it. But it's a particular way of drawing that tree. First of all, it's all vertical lines. And secondly, with a kind of sort of pseudo time element. And if you now read off this way, you could say, okay, the first two things that merge with these two, then these two, then these two, and these two. Something that you wouldn't get from just a tree. Because a tree version of this drawing would look something like this. You have A and B here. And maybe C would be here. And then D would be here. Then I might draw E. Now this could be arbitrary. I could draw it many different ways actually. So what I'm doing right now. And then H and I, and then J, and then G maps to J.
You are saying what information the dendrogram provides that you cannot get it from the tree? The order of the merge? Yes?
It's at least the order of the merge. It'll actually end up being something more than that.
But you can get the order of the merge from the tree.
You can?
can.
So which merge first, this or this?
But they are independent. As in they are not inside each other.
Are they? Are they independent? If this was the actual merge process, this said that A and B were much closer than E and F. That's why I merged them first. In fact, the blob AB was closer to the blob C than E was to F. That E and F are actually quite far away when they merged. But in this, I have no way of telling that. They may be independent in words they don't affect each other. But you have lost information in terms of knowing is this cluster the same quality as this cluster?
Right.
That's the point.
That's right. In the datagram, you can get get this relation between even pairs of different clusters. But
Yes.
in the tree, you can just get this information among the pairs within each cluster. Like
Right, you can know, for example, that this
A and
blob
B
is
are-
smaller than this blob, which is
Right.
smaller than this blob. So along a path, you can get that information. You can't get the information across paths. There was a comment from yeah.
I don't get the idea.
Because I haven't defined it properly yet. So, but yeah.
Why we cannot get the order from the tree and then?
No, I'm not saying you couldn't augment the tree with further information to provide you with that. I'm not saying that. I'm just saying if you just draw any tree, if I didn't tell you what dendrogram, I just do this for you. This would be a perfectly valid representation of the hierarchical clustering. But I want to point out that it's missing certain information. You can put it back in there, and then you'll get that.
Because what I'm seeing, like the dendrogram is exactly, the tree is exactly similar to dendrogram.
But what about the point I just made from Lena?
That's why I didn't.
Okay, so
Instead of a straight line horizontally, you directly connect the nodes to the point. It is the same as
sorry.
you're basically drawing horizontal lines.
Yes.
Then drawing the
Yeah.
Instead, if you directly connect the nodes to the point, it is the same as tree.
You're saying I should have just done this.
Yeah.
Then it would be the same thing.
Of course, it's the same. How it's so hard to understand.
Sorry. I sense a certain amount of frustration in the room. Would you care to explain?
Oh, it's been clear from the very beginning. So.
Oh, good. I'm sorry I'm boring you. So,
But you can add extra information to
yeah.
make it even different than what you think. I mean, so for example, you're writing the branches vertically to
Yeah.
designate a length.
Yes. That's my point.
Right,
That is,
and
that in fact is more. In fact, what you're going to do is provide even more information than I've drawn there. This is good. Because I just said you want to have them in some order. In fact, you're saying put a length on it.
Right.
And let that length mean something.
Because, I mean, it could just be a peculiar level structure.
Yes.
But
Yes.
it's way-
Okay, so if you think these are exactly the same, I want you to explain to me again how are you going to distinguish this merge from that merge. If you say they're the same merge, I'm telling you that they're not, because this merge happened a lot later in the process. So you need to tell me how this tree has its exact information in it.
How can you define that this merge EF happened after the AB?
Because now we get to the real point. I haven't even bothered to define how to construct a dendrogram. have I? So let me actually tell you how to do that. I mean, the basic idea of a dendrogram construction is you look at your merge sequence. Right? You start at the bottom, you assume so this is another issue. How do you make sure the points are ordered correctly so you don't have crossings? We'll forget about that. Assume they're ordered correctly. Right? So you start from the merge sequence at the bottom. So let's say you have a grid if you want, right? Just to make it simple for now. So you don't have any actual notional length, you just have ordering. So I have a grid. Okay? And now I say that the first merge happens up to level 1. The next merge that happens must go to level 2. The next merge that happens must go to level 3. And just keep doing that. So there's the first merge is level 1. This is level 2. This is level 3, 4, 5, 6, 7, 8, 9. What have I got here? And in fact, I could draw these trees in many different ways. Let's see. A dendrogram is a particular choice of drawing. It's a particular visualization choice.
Yes.
That's what I'm trying to say. Combinatorially, yes, they're identical. We're not talking combinatorics here. We're talking of the visualization. Yes.
Are they always planar representations?
Cases where you
There always exists an ordering which will guarantee this is planar because it's a tree. There's no.
But I mean, when you want to, represent it in a non-planar way to pack more information.
Why? So if it's a
Oh, I don't
hierarchy,
know, just 'cause-
if it's a hierarchy, then why would you have hierarchy is a tree? So any tree is.
No, but I mean, just would you want to render it in some way to encapsulate some other information? I can't.
You might,
imagine
although a
that
non-planarity is something that sort of is bad for visualization, unless that crossing is capturing some meaning. So generally, no, you don't want to do that. You want to keep the order crossing free. So yeah. So I mean, there are. I mean, in general, if you want to represent a cluster, you can imagine something that has crossing. But again, you're trying to avoid it. Yes.
So it's the level of the merge by which the merge order is defined. Yeah, in the random one. Is it?
The merge order defines the level. The other way around.
Okay.
The merge order of the clustering defines the level at which you draw.
Whichever gets merged first,
Yes.
that will have the
Yes.
lower.
And as Todd was pointing out, you could be even better. You don't have to have a grid. You could actually have a length. You could have a notion of time or a notion of distance. You could say, I put them at a certain level based on the distance when I had to merge them. If, for example, you're doing a filtration, you're doing persistence. So persistence diagrams, for those of you who have some familiarity with computational topology, look like this, in the sense that you have a parameter, a scalar parameter, that represents sort of topological time in some sense. And as that time parameter goes along, when merge happens, you plot it at that point. So these will be highly non-uniform. You will not have an even value. And this, in fact, this is exactly what is used in evolutionary biology to build phylogeny trees. Because the distance matters here. Here you want to say that things that have a large edit distance apart are further apart in the evolutionary tree. Right? Things that are closer are lower down the evolutionary tree. So these distances matter a lot. And so that's why dendrograms are so popular.
Whereas we don't have any notion of distance in the tree.
You only have a combinatorial description of the merge. So so that's what you're saying. You can order the merges in a partial order, right? That this merge happened after this merge,
Yes.
but it's a partial order. What you're doing is converting this partial order into a total order based on the merge sequence. And the dendrogram gives you that total order.
I suppose you can also look at the length horizontal, not just vertical.
Yes, you can.
Or
You can.
like the sparsity or the diameter.
Absolutely, and I'm not sure what the right encoding channel is, to use Mariah's term, right? What the right encoding channel is for the horizontal length. What would be a reasonable thing here? Usually when I've seen dendrograms, they've been kind of evenly spaced horizontally, depending on the size of the layout and stuff. But I'm not so. What would be reasonable in terms of horizontal thing?
What do you mean?
Well, can you encode information in the horizontal? We're only encoding information in the vertical intervals. These are all evenly
So
spaced.
like, let's say the diameter of the things that they put together, or the drops.
Yeah, you could do that.
Or some other type of measurement of how.
Except that then you'll be forced to be able to embed the original metric into the line, which is not always possible.
What do you want to import?
No, it could be encoded something there. No question. It's a channel. It's a visualization channel. What can you encode into the channel? Is the question.
The vertical height and the horizontal distance if they match, you could get the same information.
But then it's the same. You're not adding anything to it. So anyway, so hopefully I've been able to argue that a dendrogram actually does have information in it that is missing from a purely combinatorial representation of the merge tree. From the point of view of algorithm analysis, the merge tree is sufficient. But if you want to capture timing information of when these things happen, right, the dendrogram gives you a lot more information than you get from it. And that's why these are, you will, in the literature, especially in biology, is rife with hierarchical clustering and dendrograms and issues. I'm not sure why it's called a dendrogram. I think it's something to do with these fingers.
Neurons. So dendrites.
Dendrites, neurons, probably that's why, because it's after all biology. Yeah, that's probably where it came from.
Could also is the thickness of the line.
Yeah, so the thickness is. Yeah, I don't know if you could do anything.
How big of a merge was it?
Yeah, so that's the thing, right? If you want to say that these two merges are big clusters coming together, you could imagine a big thick thing up there. And I've seen that happen in some of these phylogeny things. So there are things you can play with. And again, my point is that a lot of working clustering boils down to how you can visualize the answer. This is not something that people like to think much about. We prefer to think about harder things like how do you design the algorithm, how do you analyze it. But this is important, and this actually drives the use of these methods. So if you have a new clustering algorithm, you want people to use it, probably the best thing you can do is come up with a good way to visualize the results, and then people will start getting using it. And we'll talk about it. All right. Any other questions? And this is basically all I have to say about hierarchical clustering. So I want to move on to another topic for numbers. All good? Okay. All right. So originally, at least in the book, the next topic was going to be on density estimation, which is another way of thinking about clustering. But I felt that it might be useful to take a brief detour, since we're on the topic of visualization anyway, talk about how we actually can look at clusterings. Because there's some nice geometry and some nice theory and some nice ways of thinking about abstractly how we do visualization of clusterings and how we sort of embed things in certain space. So let me talk a little bit about that. So as you've all seen with your data, right, you have data in 5 dimensions, 10 dimensions, 15 dimensions, what have you, and you have all these clusterings you want to represent. And of course, if data was in 2 dimensions, I can easily draw basic points, and you can see the clusterings. But in general, you can't. It's very hard to look at the answers. And if you've ever done anything with high-dimensional spaces, even Euclidean spaces, let alone the non-Euclidean spaces, they get very strange in high dimensions. Things happen that you don't expect. Non-intuitive things happen. You know, all your volume goes off to the corners, balls look like spikes, and then weird things happen like that. So it's very hard to get a sense of what your data looks like, even if you run some analysis, some tests on it. And so you really want to be able to map things to some lower dimensional space, where either you can see it, or where it's at least more manageable. So what goes along with a lot of clustering work is the problem of what is called either, depending on the problem, embedding or dimensional aggregation. And these are, of course, two flavors. In some sense, dimensional reduction is a special case of embedding, where the basic problem is that you have your points in some space and the clustering associated with it, and you want to map it to some other space, which is kind of nice in a sense of looking at it. It's nicer. Okay, it might be easier to compute with, it might be easier to manage, whatever. It might be 2-dimensional, it might be a tree. It may not even be a geometric space. It could be map things into a tree. And in some sense, that dendrogram is a mapping of a hierarchical clustering into a tree. So you can just look at things. And so there are a lot of questions that sort of swirl around all of this that tend to go along with unsupervised learning in general and clustering in specific. So what, again, we're going to look at is the problem of embedding. Right? It's the problem of embedding something into another space. So a lot of the clustering algorithms we talked about live in a metric space. And so I have some metric space XD, right? And my output, after running through some black box, is a partition, C1 through CQ. Right? And now I want to look at this answer and see, is this reasonable? What do I do? The only way I can deal with this problem is if somehow I can look at the clusters in such a way that things that are in one cluster are close to each other, things that are in another cluster are close to each other, and things that are in different clusters are kind of far apart. And so what I'd like to do is embed these points into some space. In fact, now I'm not even going to look at the clustering anymore. There are ways to think about embedding just the clustering, but just look at the points themselves. Can I embed the points themselves into a space where things that are close in that space and I can see it, things that are far off? And if you think about it, clustering itself is a weird kind of embedding problem. Because if you think of this, you're mapping the points. So clustering is a map from the points to the set 1 to k. Every point gets labeled with this cluster. And now if you plot the set 1 to k, you get a big blob here, you get a big blob here. Kind of very easy to see, isn't it? It's not a very descriptive map, but it nevertheless is a map. But what you, of course, want to know is more. You want to know, okay, this is a good clustering. Just the fact that it got put together doesn't mean it's a good clustering. You want to know sense of dispersion, variance, all that stuff. So clustering itself is an embedding technique. So let's talk about other kinds of embedding techniques. So what might you do here? I have a metric space. All I know is that two things have a certain distance between them. What do I do? And let's say I want to embed them in for now a well-behaved space is say 2 dimensions.
You want the locality to be preserved, right?
Yeah, in some sense.
Closer points should be closer.
Right. Because I want the 2-dimensional representation to capture the distance in the original space. So first of all, maybe I can always do this. Maybe there's always a way to map things into 2 dimensions. Maybe there's always a way to map things into 1 dimension. Can you say something quickly about that? Yes or no? What's your gut feeling? If you're going to lay a bet on whether you can always map a metric space into 1 dimension or not, what do you bet? Huh?
I think
No? You can? Good. So we have a disagreement. So how? Tell me how if you can.
I mean, we want the distance to be preserved, right?
Yes.
That's
Yeah. So the distance between 2 points in one dimension should be the same distance. So tell me how you do. Yeah, you just said you could do it.
In one dimension,
I
right?
didn't think about that point.
The one dimension part?
Distances will be preserved.
Oh, so well, I can always map anything I want.
Yes, then we can get anyway.
So are you changing your mind?
Yeah, let me
Are you
think-
retracting?
to think more.
Or you're backing away violently?
I think more.
Anyone else? Yes. One
But the
dimension.
best distance that you can preserve if you want to project to one dimension is that you project data point to the first principal component, right? Along the most variance. I mean, along the direction which has the most variance.
This would be great, except I don't have directions.
SVB?
I have a metric space. I don't have any directions. I don't have coordinates. I don't have matrix. Sorry. Now what do I do?
Yeah, I didn't understand something here. You have the data points?
No,
you're
I have
saying-
a metric space. I have distances.
So it's
Oh,
I
you
think
have
it's
the
hard.
distances.
That's all I have. Yeah?
It's hard. It cannot be because
It cannot be done.
Let's see. You have one point here, and you have one point here in this direction. Okay?
Yeah.
And you have here one there. Because you have distances over there, and you have only one dimension.
Yeah.
So a lot of points. Let's suppose these 2 points are. These
Can we draw an example? Okay, let's make it even simpler. Give me an example in 2 dimensions that you cannot draw in 1 dimension. Yes, tell me. What
I mean, it's hard to
tell me.
draw in 2 dimensions.
Yeah. What you just drew?
Just one point and then another point on that same line, and then put like one in between them, but slightly down, because now.
An equilateral triangle.
Yep.
Okay. There are 3 points, all at distance 1 from each other in 2D.
That's not happening.
2D has not happened, right? In 1D, you can only have 2 points at distance 1 from each other. There's not enough room. In fact, think of a d-dimensional simplex, a d-dimensional tetrahedron. There are d points or d plus 1 points all at distance 1 from each other. There's no room. There's just no space. Exactly. There's just nowhere to fit in. Okay, so we already have a problem. We can't fit stuff. And this is true for 2D. If you have points in 3 dimensions, you can't fit them in 2D. If you have whatever, so any fixed dimensional space, if you have things in a higher dimensional space, you can't even map it there. So now it seems completely hopeless. We can't do anything.
It's not hopeless.
Good. There's hope. Give us hope, Kevin.
Because the point, the dimensionality of x, we don't know whether that's really, it's most likely much higher than the rank of x.
Okay, but I'm sorry, I'm not allowed to use the word dimensional. It's a metric space. Sorry, but the rules are the rules. I have a metric space. What do I do now? All I have are distances.
Maybe I can use a better distance.
Use a better distance. What do you mean? You change the distance?
Maybe I can find maybe I can find a better distance in a different metric space. I think that's,
Ah, but then you're doing an embedding anyway, aren't you?
yeah, it's embedding.
So
What-
how do you do it though?
How do you do it?
How do you do an embedding? I mean, what if someone said I need to do this, give me a way to do it. You know it can't be done exactly. So what might you try to do? So map points from a metric space x comma d into a particular metric space. Let's say a nice one. Let's say it's Euclidean space. Let's say it's 2-dimensional Euclidean space. Right? So we'll just write it L2. Okay. So every object here needs to have a map into 2 coordinates here. Okay, so let's say there's some map. So there's some map that takes fx and gives you some oh, it's horrible. Sorry. This is called x1, x2. Okay? We know that we want the distance between x and y here to be something like the right? So what do you want? You want to preserve the distances. But we know we can't do this exactly, which is why I put this here. So this leads us, this very question. Again, what does it mean to kind of sort of do it, and how do you do it? To this place of what what in my line of work we call metric embeddings, but out in the sort of more general data mining sort of area, people call multi-dimensional scaling. And keeping with the grand tradition, MDS refers to both the problem and one particular algorithm for solving, which annoys me to know it. But this is the problem that people have. And if you start, looking around, you maybe come across this, how to visualize, come across a single MDS. It's a problem of how to take data that lies in an abstract distance space, described only by some kind of matrix. So you can think of some kind of matrix of distances. So I said there's no matrix, there's no matrix of coordinates, there's a matrix of distances. And how to map it now from the matrix of distances into a collection of coordinates, x1, x2, x prime 1, x prime 2, so on. Such that this is kind of roughly approximately preserved. And again, depending on who you ask, there are different ways of thinking. Some people think of MDS as the case when this in fact is a Euclidean space, but it's very high dimensional, and you want to map it to a low dimensional space. Some people call this a metric MDS when this is an arbitrary metric. Some people distinguish the case when this distance metrics may not be a metric. There are all these different sub-cases here, just historically how they came out. But fundamentally, they're all the same question. How do you do this? Yes?
So if we cluster them, then hopefully these are groups that are closer together.
Yeah.
And then maybe we can use those clusters to look like if we have some four-dimensional space, if we can construct 3 clusters, can we use that to find some kind of small
So in fact, that is a sub-area of this called supervised dimensional reduction. And it's supervised because your clustering is telling you that I only care to make points that are close to each other, and the points that are far should be far. Other than that, I don't have to preserve all the distances. Right? As long as I have some notion of close and far, I can be very skewed with this. So if you now are willing to change this definition to capture that, you get into this supervised realm. So there's something called linear discriminant analysis, called LDA, not like the other LDA, which is latent tertiary allocation. And there's also Fisher discriminant analysis, which is FDA, not like the other FDA, which is and there are other methods like that will say, give me a way to embed this so that I only embed the stuff I care about. The things that are close, things that are far, far. So yes, there's a whole literature on that as well. For now, we're not going to talk about that, but be aware that it does exist, and maybe when I talk about sort of supervised clustering, I might talk a little bit about that. Because there is a kind of notion of supervised clustering. But yes, that can help you guys. So sometimes I'm doing a bait and switch. I start off by modeling it by clustering, but really I'm just talking about the basic question of how to embed points in a lower dimensional space. So there are many ways you could think about doing this problem. And so one particular approach that has been very popular in the algorithms community has been to say the following, that I'm given some distance metric. So let's say I have some mapping, let's say goes from the metric space, right, to Euclidean space, and this could be any dimension space for now, only in 2 dimensions. What I want is that these things are close, and the way I would define close is by taking ratios. So I'm going to say that first of all, number one, that these, let's say just to make it easier, these mappings are contractive, so the distance always gets smaller. So we'll say that fx minus fy is always less than or equal to dxy. And secondly, I want that this ratio fx minus fy divided by dxy. Now it's always less than 1, but I want to be close to 1. So I want it to be greater than or equal to some. Yes?
Mapping is always contracted, right?
Could be. You could scale things up and down. Right?
No, if you are scaling down,
If I'm scaling down, it's contracted.
then it's always contracted.
Well, I don't know what scaling means. So
I mean, if you are
what is scaling in a metric
high
space?
dimensional space, you are handling the points into low dimensional space. That is still data. For the case of
No, that's true if you're doing a projection. That's not true for any mapping. I can do some nonlinear mapping from 3D to 2D, which blows everything up. I didn't say
Where
this
distances
mapping.
are present.
No, but what I'm saying is just the fact that you're going from high dimensions to low dimensions doesn't necessarily mean the distances get smaller. If you're doing a projective mapping,
Yes.
then the distances get smaller. But that's a very specific kind of mapping. I'm not doing a projective mapping. I'm doing any kind of mapping.
So in this case, we cannot say whether.
Yeah, that's what I'm saying. I'm going to make it a condition, just to make it simpler. You know, the reason why I do this is because this ratio could be either negative or could be less than
Yes.
1 or more than 1. It just makes it easy. There's no real reason why you have to. Most of the standard mappings are. And so you could ask this question, and you could say, okay, what is the best I can do for any metric space at all? I have, say, a distances between vertices in a graph, right? And I want to embed this into some low-dimensional free space. What can I do? Can you do anything at all? And in some sense, the surprising thing is that you can actually say something. And you can say something very powerful. In particular, what you can say is that for any metric space, and this is a result from 1984 by Bourgain, a very famous mathematician. For any metric space, and for now we'll just do the finite metric spaces. There are these infinite metric spaces. So every finite metric space. So this is a notion of n. So the x is equal to n. There exists a mapping into Euclidean space with roughly log n dimensions. Okay, such that the distortion, so we'll call this thing the distortion. Okay, so the distortion, and I should have written this as, just to make it easier, 1 over alpha, so alpha can be a number that's bigger than 1, okay, is okay, so just let's parse this for a second. What this says is that if you want to embed an arbitrary metric space with n objects in it into Euclidean space, the amount of room you need only be log n dimensions. Okay, so if there are n points, you need only log n dimensions, and the distortion you will pay will be log n. And both these things are tight. You cannot do any better. Construction, there are certain kinds of metrics you can construct from graphs called expanders that do not let you go and do any better than this. Now it's a little hard, at least in my mind, to sort of explain the intuition behind why these are the right numbers for this. Right? I mean, there are proofs, but they don't give it a good intuition. This log n though this shows up in many places, and we'll see more of this later. And this distortion is not great. Like I said, you can prove this, you can't do any better than this. And in fact, if your metric space has some better structure, you can do a little bit more. So for example, suppose instead of any finite metric space, this is result 1, right? So suppose it's the same thing, but instead of any finite metric space, it is any set of points in L2 for any dimension. I don't care what the original dimension. Then the same thing holds. There exists a mapping into L2 O log n, but now the distortion is arbitrarily small. I can make it as small as I want, as close to the exact value. The price you pay, of course, is that this dimension goes up, something like this. You may have seen this in any number of classes that Jeff and I teach. It's called the Johnson-Lewis-Russell lemma. If you're not familiar with that, this will. And the cool thing about this result is that, so it's a stronger version of this, right? This is saying, okay, for any metric space, you can do this, but you pay this much distortion. This is saying, no, if the points, you know the points come from a high-dimensional Euclidean space, which is one form of MDS that people look at, you can do much better. You get the same dimension, but your distortion is way better. Because somehow, the fact that they're already in Euclidean spaces makes life a lot simpler for you. And it doesn't matter what dimension. It would be an infinite dimensional space. All that matters is how many points there are. Some of the points themselves carry enough information between them that within log n dimensions you can do all this. Right? And there's a whole bunch of results of this kind saying, okay, if you change this from that general result, can you do any better? There's a whole host of results. I'm not going to talk about it because most of them you'll never encounter. You don't really need to care about them unless you really care about this question. But there's a whole this whole area is called metric embeddings. This area of algorithm analysis, and it's a very fascinating area of things you can do in these cases. Like how do you map from one space to another? Can you go from L2 to L1? Can you go from L1 to L2? Can you do, this is by the way called a dimensionality reduction result, because these two are the same space, there's different dimension. So there's a very special case of metric embedding called dimensionality reduction. Okay. So in some sense, we already have an answer to our first question. If we invoke this result, we get a mapping. The way we do the mapping is kind of bizarre and interesting. I won't give you a proof, but I'll just tell you how it works. It's not anything you'd expect. It's extremely dumb in some sense, but yet it works. And what you do is you say, okay, I have a metric space. All I have are distances. I have very little at my disposal here. I can't do SVD, I can't do projections, I can't measure angles, I can't take directions. But here's what I can do, I can sample. So what you do is, you sample a set of size roughly log n from x. Okay? So that's some set x1. And then do this a whole bunch of times. You do this, in fact, log n times. Is there a log squared n these results? Remember the Boolean result? You guys remember this? I always forget, because for a Euclidean space, a log squared n can be pushed back to log, so sometimes it doesn't really matter. I always forget whether the log squared n. I think the original result, you need log squared n on these things. It's actually log squared n. So you sample these sets of size log n, okay? So now I have log squared n of them. Now for each point x, you make this, what I have to do? I have to make a coordinate vector, right? So I have to construct coordinates, log squared n coordinates. So for each point x, the ith coordinate of x is going to be the distance from this to xi. So I'm going to take that set of size log n, I'm going to measure the distance of x to that set of size log n. The closest distance. That's what it means. And so for each x, I get this coordinate vector of length log squared. And then you can show that this property. This takes a bit of proof. It's not easy at all, but you can show this property. So it's a very trivial algorithm. It doesn't do anything at all. It just samples points and measures distances to points and writes all these numbers.
Can you explain it once?
Yeah. So what you do is you start off by saying, sample a set of size log n, write it down. Sample a repetition of a set of size log n, write it down. So you get these many sets, each of size log n.
You do it for log squared.
Log squared n times. Okay? Now for any point in your metric space, you have to map it into this L2 space. To construct the ith coordinate of that mapping, you look at the ith set you just constructed and measure its distance to that set. And you write it down. So now each you get so this is basically d of x comma xi, this is d of x comma xi plus 1, and then so on. So that's the coordinates for the first point.
So
And do for the next point, and the next point.
and xi lies in the lower lines. Reduced lines.
Well, xi is just a number. But the vector of xi lies in log squared n dimensions because there's only log squared n on these sets. Right? And then there's a lot of work to show that the distortion is going to be only log n. It's not obvious at all, but you can prove it. So that's it. That's your embedding vector. So it's a weird kind of data independent embedding, right? The algorithm is fixed, doesn't look at the data at all at numbers. So it works regardless, but also that means in practice it doesn't work that well. It just gives you a worst case model.
Excuse me, so you said that you take the distance between xi and what's the other letter?
No, the coordinate, the new coordinate of small xi is the distance from that original point x to that subset.
Just okay, minimum.
So the distance to a point of subset is a point and a subset
Overall.
Yeah, no, the xi is the closest.
Oh, okay.
That's all I had at my disposal. All right. So I think that's enough for today. We'll continue with MDS and other methods of doing MDS, especially very popular ones, next lecture. But just keep this in mind that this is a whole area of how to embed things, and we'll soon see how to embed things into 2 dimensions and what you can do with that.